In any case, it's a great pleasure to be here today to be able to talk to you about spatial graph theory, which I'm guessing most of you don't know about. So I want to talk about the history of the field. So it actually has its roots in chemistry. And the idea was that chemists often propose what they call targets of synthesis, which are structures that can't be synthesized with known techniques. And they use these targets to stimulate development of new techniques. So there was a target of synthesis, which was a molecular knot that was targeted for 100 years, almost 100 years, before it was eventually successfully synthesized in 1989 by Jean-Pierre Sauvage. Another example of such a target of synthesis was a molecule in the form of a Möbius strip. This was a target of synthesis for over 60 years, and eventually in 1983, David Walba at the University of Colorado created such a molecule by first creating a ladder with 3 rungs, which I show, oh, I don't know if that will reach there, which I show up there, and then forcing the ends of the ladder to join together. And he wanted to show that the ends of the ladder had joined with a half twist, but the molecule was too small to see in a microscope or even to see with electron microscopy. So in order to show that they had joined the way he claimed they joined, he had to do experiments proving that they had properties that you would expect for a molecule with a twist like that versus one with the ends glued straight. So they used NMR data to show that the molecular Mobius ladder, as it was called, had a 6-fold symmetry. So we can see this symmetry in the slide here. If you look at the molecule, then I've sort of drawn it in a stylized way without all the oxygens and all of the little corners which are carbons, so that you can see it. The numbers don't do anything except for help us follow this. So we're going to rotate this molecule by 2 pi over 3 according to the arrow that I've drawn there. And when we rotate it, you can see that number 1 goes to 2, 4 goes to 5, etc. But what happens is that the twist also goes on the side, because you rotate the whole thing, and the twist is there on the side. But in order to say that it's a symmetry, it has to end up looking exactly the same as it was to begin with. And so we twist the molecule itself to end up looking like the picture on the right there. So this gives us a 6-fold symmetry, because you can see that number 1 goes to 2, 2 goes to 3, 3 to 4, etc. And so if you do this 6 times, every point will go back to where it started. However, this symmetry is not a rigid motion of R3. So what you see here is there's a rigid motion of a 2 pi over 3 rotation, but then that moving the twist around is not a rigid motion. For those of you who know what S3 is, it would be a rigid motion of S3, but the molecule lives actually in R3 and not in S3. So, well, maybe we think it lives in S3. So this proved that the molecule was flexible. The fact that it had a symmetry that couldn't be induced by a rigid motion must mean that it was flexible, at least somewhat flexible, in order to be able to move this twisting as it did. Then they went on and used experimental data to conclude that the molecule was distinct from its mirror image. And what we can see, if you look at this, the untwisted ladder and its mirror image, they're exactly the same. The untwisted ladder and its mirror image are exactly the same. So that tells you that the molecule didn't join straight without any twist. But that doesn't mean it joined with a twist. Maybe it joined with multiple twists or in some other crazy way. So we want to know that the molecule that looks like a Mobius strip, the one I've drawn at the bottom, actually is different from its mirror image. So here you can see the molecule and its mirror image, and the only difference between those pictures is the twist in the front. So in one case, the overcrossing of the twist goes down, has a negative slope, and in the other one, the overcrossing goes up. So that's the only difference between those molecules. So the question is are those 2 molecules different? Or could one become the other? And this is more complicated because of the fact that the molecule is flexible. So you can't just say, well, could I rigidly move one to the other? You have to consider all possible ways to deform one to the other. So the first thing, I have to have a drink. The first thing we might consider is a Mobius strip. And it's well known in topology that the Mobius strip can't be deformed to its mirror image. So here you see the Mobius strip and its mirror image. The only difference between those is, again, the twist in the front. But the thing is that a ladder isn't a surface. So it can move in ways that a surface can't. So this doesn't show that the molecular Mobius ladder actually doesn't change into its mirror image. And in fact, here is a deformation. So the first thing I do is I draw it with just numbers, without all the carbons and oxygens, and I'm going to show you the deformation of it to its mirror image. So the first thing I'm going to do is I'm going to rotate the molecule so it's vertical to make it easier for us to see this. Then I'm going to grab the edges 2, 5, and 3, 6 and move them up and forward, as you see going from the first image to the second image. And then in the second image, you can see that there's a long arc going between vertices 3 and 4. And I'm going to grab that and pull it to the left so I get the next picture with the green on the left. And in addition to that, I'm going to look at vertex 5 and slide it up so it's now above 2. And so you get this picture at the beginning of the second line. After that, I'm just going to shrink the edge going from 1 to 6 so that it looks like the picture on the right. Now you'll see that I highlighted a kind of 8 shape in blue because that's going to help us see the next step. So in the next step, I didn't really do anything except for take that 8 and make it nice and round so it really looks like an 8. So that's the third step. And now I'm going to grab vertex 3 and 4 and push them back behind the screen so that I end up with these two sort of like a twisted circle around itself. And then I have 1, 6 becomes a vertical edge, 3, 4 becomes a vertical edge, and 2, 5 becomes a vertical edge. So what you can see is that we have exactly the same graph that we started with, except the twist has the opposite slope. So you can see in the first one, the overcrossing is going up, and in the last one, the overcrossing is going down. So we have actually deformed the Mobius ladder to its mirror image in a way that we couldn't have deformed a Mobius strip to its mirror image, no matter how flexible it was. However, one thing you should observe about this is that if you look at the rung, well, I call it a rung because it was on a ladder, the rung 1, 4 or 3, 6 in the first picture, and you look at the edge 1, 4 and 3, 6 in the second picture, they went from being these vertical rungs of the ladder to being part of the side of the Mobius strip, if you think of it as a Mobius strip. So that's an interesting fact. And what it turns out is that this means it's chemically impossible. Because in fact, those vertical rungs of the ladder are carbon-carbon double bonds. And the sides of the ladder are this long chain of carbons and oxygens. And so if you see the green here, if it were the case that you followed this deformation with the molecular structure, the carbon-carbon double bond in the first picture would have to go to this long chain of carbons and oxygens in the second picture, which clearly it can't do on a molecular level. So in fact, even though I've shown you that actually there is a deformation from the Mobius ladder to its mirror image, which couldn't be there in the Mobius strip, it doesn't mean that the molecule is the same as its mirror image. So this sort of leaves us back where we started, with the question of, is it true that the molecule can change into its mirror image, even assuming it's completely flexible? So in 1983, John Simon, who's a topologist at the University of Iowa, used knot theory to prove that in fact a Mobius ladder with the rungs and sides distinguished as they have to be for this molecule cannot be deformed to its mirror image. And I'm going to give you a sketch of that proof in a second. And this is what's considered to be the birth of spatial graph theory from the point of view of chemistry. So here, chemistry gave birth to spatial graph theory. But now let's go on to try to understand how Simon did this, but first we need some definitions. So a molecule is said to be chemically achiral if it interconverts, if it changes to its mirror image at room temperature. Otherwise, we say it's chemically chiral. Now, this word chiral or achiral is going to be important for the rest of my talk, and so I want you to remember it. But the problem is nobody ever remembers it, and the reason they don't remember it is because of the letter A. So everyone is used to the letter A meaning not. So for example, if one person's political and another person is apolitical, the apolitical person is not political. So we expect these definitions to be the reverse. We expect chiral to mean it's the same as its mirror image, and achiral to mean it's not the same. But that's wrong. And the way to remember which is which, because it's easy to get confused, is to think about the etymology of the word. So the word chiral actually comes from the ancient Greek word chi epsilon iota rho, which I'm not going to attempt to pronounce, in particular because I gave a talk where I tried to pronounce it, and someone who actually spoke ancient Greek told me that I was doing it wrong. So I'm not going to do that. But in any case, it came from this word, which in ancient Greek means hand. And the reason it came from this word meaning hand is because you can't take a left hand and change it into a right hand. No matter what you do, your hands are always distinct. So we're thinking that chiral means like a hand. It's a positive characteristic, like a hand. And so achiral means not like a hand. So if you keep that hand thing in mind, you won't get confused as I continue. All right, so that definition, let's have a look at that definition, is about the behavior of a molecule. It's not about anything mathematical. It's something you can tell experimentally. Does it change into its mirror image or not at room temperature? We, as mathematicians, want a mathematical definition. So I'm going to say a molecule is topologically achiral if it can be deformed to its mirror image. Otherwise, we say it's topologically chiral. And again, we're using chiral to mean like a hand. So, and the reason we have the word topologically here for students who might not have ever heard of topology is because topology is the study of deformations. So for example, this water bottle that I like to drink from is a topological water bottle. This water bottle is a geometric water bottle. I'm a topologist. I drink from the topological one. In any case, so if a molecule is topologically chiral, that means it can't be deformed to its mirror image. If it's chemically chiral, it's chemically distinct from its mirror image. So if it already can't be deformed to its mirror image, chemically, it will definitely be distinct from its mirror image because whatever the molecule can do, it may or may not be rigid or partially rigid, is going to be some kind of deformation. So topologically chiral implies chemically chiral. And here's a picture of where don't mean the same thing. So you should realize, for those who haven't taken chemistry or haven't taken chemistry in 30 years, as I haven't, more than 30, anyway, the black triangle comes out at you. The striped triangle goes behind the screen. And then the little straight line is in the screen. So this is a very small molecule, and in chemistry, the smaller the molecule in general, the more rigid it is. So this is a rigid molecule, and I've drawn it and its mirror image. And what you can see is that they are different. If you take the original and you turn it, remembering that it's rigid, there's no way you can get it to be the mirror image. On the other hand, from a topology point of view, I can grab the H and the CO2 H and just like yank them in the back around the middle vertex, the middle carbon, and go until it gets to be in the position of the mirror image. You have to make that noise when you're doing that. Okay, so this shows that the molecule is topologically achiral, but chemically chiral. So this shows you that these concepts are not exactly the same. We should say, however, that molecules which are chiral, chemically chiral, but not topologically chiral, like the one we just have here, have the property that if you heat them enough, they will switch into their mirror form. Whereas molecules which are topologically chiral, no matter how much you heat them, will not change into their mirror form, because to change to their mirror form, bonds would have to cross through each other, and that's not going to happen. So this tells us that topological chirality is a property that chemists are interested in knowing about. And so in general, apart from a Mobius ladder, which is still waiting for us to prove it's chiral, this is a generally interesting designation for chemists. All right, so let's go back to the molecular Mobius ladder, and I'll give you a very brief sketch of how John Simon proved that it was distinct, topologically distinct from its mirror image. So in other words, that it's topologically chiral. So the first thing we're going to do is we're going to represent it in this sort of symbolic way without all the carbons and oxygens. But we have to make sure that we're not going to mix up the rungs with the sides, because we already saw it could be deformed to its mirror image if you allow those to be interchanged. So we're coloring the rungs differently from the sides. Now the yellow, purple, pink, there's no difference between them, they're just helping us see it. But the blue has to go to blue. It can't go to a non-blue color. So, and we're proving it's topologically chiral, so we're going to assume it's completely flexible and still prove that it can't change into its mirror image. So the first thing we're going to do, it's completely flexible, so I can just grab the blue and open it up flat into the plane, which causes the red, yellow, and purple to stretch out in these big arcs, as I've shown here. Just like if you had a rubber band, you could take one twisted and untwisted and flatten it out in the plane. So from that, we're going to get the twofold branch cover. Here, I am not giving you the formal definition of that. This is just the intuition. By gluing two copies of our picture together along the blue circles, aligning the rungs of the same color so they match up. So what you can see is I have these two pictures of the opened out circle with the arcs, and in both of them, the red is on top, the purple is in the middle, and the yellow is in the bottom. So the one on the bottom, you can think I just like punched it down, but I didn't change the order of the rungs. So then I glue these two copies of the same thing together along the blue circle, and I get the picture on the right. And we call that the twofold cover branched over the blue circle because there are two copies of everything except for the blue circle. So the blue circle is a kind of singular set. Again, I'm not going to go into the formal definition of this. Okay, and then what we do is we remove the blue circle, and we now have a link. So knot theory has existed for over 100 years and has all kinds of techniques to prove that things are different from their mirror image. And so John Simon was able to use knot theory to prove that this link is different from its mirror image. And then to trace that back to say, well, if the original Mobius ladder were the same as its mirror image, then we could deform it to its mirror image, and that would give us a deformation in the branch cover of the link to its mirror image. So from this, we can conclude that the Mobius ladder is topologically chiral, and hence, as a molecule, it's also chemically chiral, which is exactly what the chemists wanted to know to confirm that the structure that they had synthesized had a twist like a Mobius ladder. So once a chemist knows that a molecule is chiral, he or she wants to know whether related molecules are also chiral. And so one term you may be familiar with if you took a chemistry class is the term isomer. So two molecules are isomers if they have the same chemical formula but different molecular graphs. Well, that has some relationship to the original, but that's not a topological relationship that we're interested in. But there's also a definition in chemistry of stereoisomers. So two molecules are stereoisomers if they have the same formula and the same molecular graph, but their graphs are embedded, that is, put into space differently. So the word stereoisomers, the stereo comes from three-dimensional, the term three-dimensional. Like your stereo, back in the day, we had stereos. So here you have an example of stereoisomers. You have the knotted molecule and its mirror image. And you can see that they're mirror images because all the crossings are reversed. So every place where the blue goes over, the red goes under, and vice versa. And these are stereoisomers because one can prove, again, using knot theory, that one cannot be deformed to the other. So they're different embeddings in space. Here's another pair of stereoisomers. So the knotted molecule and an unknotted version of the same molecule. So I had to sort of squish it with this accordion-like thing on the sides to fit. But in any case, it's got exactly the same structure, but it's embedded in space in this unknotted way. And we saw that the knotted molecule is topologically chiral, but anything that's just a plain circle can lie in a plane, and so it's exactly the same as its mirror image. So the knotted one is chiral, and the unknotted one is achiral. So this shows us that chirality is not, in general, preserved when we change the embedding of a graph, as we have here. So I want to now move from the chemical motivation to spatial graph theory more generally, where we're looking at graphs in space, but they don't have to be molecular graphs. And so just so you don't get confused, many people know what graph theory is, the study of graphs, but when you're looking at graph theory, you only care about the graph as an abstract object. What vertices are connected to what? Whereas spatial graph theory is all about how the graph is embedded in space, or even in some other space, some other three-manifold. So our definition of topologically chiral and achiral, which we had for molecules, is also true for any spatial graph. Any graph in R3 we can say is topologically achiral, not like a hand, if it can be deformed to its mirror image, and otherwise it's topologically chiral. So here are three different embeddings of a Mobius ladder, and they're all topologically chiral. Again, I'm assuming that the rungs and the sides are different, so I'm coloring them differently. So I'm treating them as colored graphs here. And so, okay, we have lots of different embeddings. You can't have a molecule, I think, like the one on the far right, but okay, still nice. But in fact, Mobius ladders can have any number of rungs. And here I've got a picture of some embeddings of M4. So Mn, n represents the number of rungs. So M4 has 4 rungs, and we have 2 different embeddings of it here. And so we can ask the question about Mobius ladders more generally. Are they the same as their mirror image? We had seen that for well, no, we hadn't seen that yet. Okay, let's keep going. Sorry. So here's a theorem that says for any n that is greater than or equal to 3 and is odd, so I've got an odd number of rungs, no matter how you embed the Mobius ladder in R3, it's going to be topologically chiral. So for example, immediately we know from that theorem that these 3 embeddings, because they have 3 rungs, which is odd, are all topologically chiral. So we're saying here that no matter what the n is, as long as it's odd, this is true. Okay, this is in contrast to circles, which can be embedded with a knot or in a planar way, where some of them are chiral and some of them are achiral. So this is an interesting property of Mobius ladders in particular. And here I have M4, here I have an embedding at the top, which is topologically chiral. It turns out that no matter how many rungs you have, if you embed it so that it looks like a Mobius strip, it's going to turn out to be topologically chiral. John Simon proved that. But I also have another embedding, which is different. It may not be obvious that it's different, but it is in fact different than the above embedding, which is topologically achiral. And you can see the achirality by rotating the molecule by 90 degrees about a vertical axis. And what happens is that you get the picture on the right, so you can see the red, purple, and green, and orange are all rotated to new positions, 90 degrees. But what you can see is that if you imagine the mirror to be in the plane where the blue circle is, then you can see that after I've rotated it, the pink rung, the pink arc, is exactly the mirror image of where the orange arc was in the first picture. And the purple is exactly the mirror image of where the green arc was in the original picture. So you can see that I've actually rotated the molecule to its mirror image. So this tells you that the molecule is in fact, this is a graph, it's not a molecule, sorry. I've rotated the graph to its mirror image, which shows you that this particular embedding of M4 is topologically achiral, because I can change it to its mirror image. And in fact, I can do this for any even n by adding one more rung up above and a rung 90 degrees away from it down below. So you can extend this to any even number of rungs. So I'm going to introduce a definition here. If every embedding of a graph is topologically chiral, as we saw for M3 it was, or any n odd, then we're going to say that the graph is intrinsically chiral. And what that means, intrinsically chiral, means that the chirality is intrinsic to the graph and doesn't depend on the particular embedding of the graph in R3. So we've seen that Mn is intrinsically chiral if and only if n, which is supposed to be greater than or equal to 3, is odd. So this is an example of an intrinsically chiral graph. And the natural question comes, well, are there other? I mean, this is Mobius ladder. It's a very specialized graph. Can we get other graphs which are intrinsically chiral? And here I have a theorem which says every non-planar graph with no order 2 automorphism is intrinsically chiral. So non-planar is the same by Kuratowski's theorem as a graph that contains K5 or K33, which I've drawn at the bottom there. Okay, so here's an example. It's a molecular example, not to say that all examples have to be molecular, but I like molecular examples. So this is a fullerene, which has what's called a cap, a CTV cap. And I'm illustrating in this picture that the graph contains K33. So you can see the weird thing that is a backwards 2. And the reason it's a backwards 2 is because it's on the back face of the sphere, and we're looking at it from behind. And so I've drawn the K33 graph in the middle so you can see how it lives on that fullerene with the cap. And then I've illustrated on the side so you can see it's a K33. What you can see is that this graph has an order 3 rotation, which you can see in this stylized picture as well. But in fact, we can prove, this is not at all obvious, but we can prove that in fact, order 3 is the only non-trivial automorphism that this graph can have. And since we now have seen it contains K33 and hence is non-planar and it has no order 2 automorphism, right away we know that it's intrinsically chiral, which means from a chemistry point of view that it and all its stereoisomers are topologically chiral. And this fullerene was brought to my attention by the chemist who synthesized it, who asked me, is it intrinsically chiral? And then I showed them it is. Okay, so now I want to move from mirror image symmetry of molecules to more general symmetry of molecules, which is also going to take us back to spatial graph theory. So why do chemists care about molecular symmetries more generally? One reason is that they help us identify structures which are too small to see with an electron microscope. So for example, we saw that with the molecular Möbius ladder. Knowing that it was different from its mirror image helps us identify it when we can't see it. So that's a reason that they care about symmetries in general, and knowing that it had an order 6 symmetry told us also that it was flexible. So we learned from the symmetries. They also help us predict reactions. And the way to think about this is think about your foot. So if you have like a right foot is a chiral object, just like your hands are. Could have thought of a hand, but I thought of a foot. Okay, so I have a right foot, it's a chiral object. I have a right shoe, it's a chiral object. The right foot and the right shoe react differently than a right foot and a left shoe. Right, the right foot is not going to be happy at all with that left shoe. So this is telling us in general the same thing happens with molecules. If a molecule has a symmetry, like for example, a sock has a symmetry, it's the same as its mirror image, then your right foot wouldn't care which sock you put on it. So the reaction of two things which are chiral is going to be different than the reaction of something which is chiral or achiral. And the same thing can be true more generally with other symmetries. And finally, they help classify molecules. Molecules are classified in lots of ways, and one way is to classify them according to their symmetries. So there are lots more reasons why molecular symmetries are important. These are just three that are sort of easy to explain. All right, so one way that chemists like to classify symmetries is with what's called the point group. So the point group is the group of rotations and reflections composed with and reflections composed with rotations. So these are the rigid motions of the graph. And this particular picture that I have here is actually, if you remember the rule about the solid triangles stick out, the striped triangles stick back behind the screen, you can see this picture as having sort of living inside of a cube, where the end of each of the F's is on the face of a different side of the cube. So you've got 6 faces, each one has one of these F's on it. And because of the fact that this molecule is rigid, its point group is exactly the same as the rigid symmetries of a cube. So that's an example of the point group. And by the way, we call it a point group because it always fixes a point in R3. So it's not like a translation, which just moves it over. So here's a different molecule. So this molecule has the peculiarity that the chlorines at the top can rotate independently from the bottom. But that's not a rigid motion. It's a rigid motion of just the chlorines, but it's not a rigid motion of space, because if it were a rigid motion of space, the entire graph would have to be rotating by 120, which it's not. So this rotation of the chlorines is not picked up by the point group. The point group is only the group of rigid motions. So for this particular molecule, the point group is Z2, because it's just a reflection, that's it. This has a reflection, it's a reflection that contains the 3 hexagons and interchanges the forward and backward chlorine, and that's it. But we're not happy about that, because we want the symmetry group of this molecule to tell us all the symmetries. And the fact that there's a symmetry between the chlorines, which wouldn't be there if they were 3 different atoms up there, if they were not all chlorines. We want that to be contained in our symmetry information. So here again is a molecular definition, that is to say it's a behavioral definition. We're going to say that the molecular symmetry group of a molecule is the subgroup of the automorphism group, which is induced, of the automorphism group of the abstract graph, which is induced by chemically possible motions, which take the graph to itself or to its mirror image. So in this example with the fluorides, in fact, the point group is the same as the molecular symmetry group because the molecule is rigid. Okay. On the other hand, the point group is not the same as the automorphism group of the graph as an abstract graph, because as an abstract graph, you can interchange any of the fluorines around the center sulfur, and so the automorphism group of the abstract graph is S6, the symmetric group on 6 points. Okay, so these are definitely not the same. All right. So we saw already that the point group of this molecule is Z2, and now I'm going to think of it in terms of the numbers I put on the vertices at the top. They're chlorines, but they have numbers to help us represent things. And so you can think of this reflection as being induced, or as inducing really, the 2-3 automorphism on the graph. The reflection, all it does is it interchanges 2 and 3. Okay, so the point group here you can think of as just generated by 2-3. On the other hand, the molecular symmetry group includes this rotation of 1 to 2 to 3, which I write as 1, 2, 3 like that. And so the molecular symmetry group is actually the dihedral group with 6 elements. Topologists call this D3. I know group theorists call it D6, but in any case, I'm calling it D3. and because all of the symmetries can be seen on the circle at the top. So every symmetry you can think of as in terms of what it does on the top. So here's an example where the point group is actually equal to the automorphism group and not, I said that wrong, where the molecular symmetry group is actually equal to the automorphism group, whereas the point group is strictly smaller. So these things are not the same in general. And you can see that with all different molecules with different levels of symmetry, you're going to have different groups, whether the molecular group agrees with the point group, which you see for the rigid molecule, where it doesn't for a flexible molecule like the Mobius ladder, where it also doesn't for a molecule with the rotating chlorines at the top, and on the bottom there's a different molecule which has two simultaneous rotations on either side. So what this is telling us is that we can't have a mathematical theory of the molecular symmetry group because we need to know how flexible the molecule is. We can't just look at it as a graph in space and immediately say what the symmetries are. So, just a second. So a mathematical characterization of all molecular symmetry groups is not possible. So what I want to do as a topologist is take a topological point of view. So the topological symmetry group, which I'm going to denote by TSG, topological symmetry group, of a molecular graph is the subgroup of the automorphism group induced by homeomorphisms of R3, taking atoms of a given type to atoms of the same type, of course. Okay, that's it. We're looking at a molecular graph, so you want carbons to go to carbons. So what you should realize is the point group acts like all molecules are completely rigid, which they're not. The topological symmetry group treats all molecules as completely flexible, which they're not. The truth is somewhere in between, and it depends on the molecule. So in general, we have this list of containments. So the point group, I'm going to think of that as the group of automorphisms of the abstract graph induced by rotation and reflections of the graph in space. Now realize that this is not the technical definition that I gave you before of chemists. It's that we're describing it in terms of automorphisms to make these groups contained in one another so we can compare them. The molecular symmetry group is the automorphisms induced by molecular motions. The topological symmetry group is automorphisms induced by homeomorphisms, and the automorphism group is just all the automorphisms. So we have this containment, and we can see that the molecular symmetry group is wedged between the point group and the topological symmetry group. Okay, so now, just as I did with chirality, I want to leave the realm of chemistry and move into graphs in R3 more generally. So we can think of graphs as graphs in R3, embedded in R3, as a natural extension of knot theory. Knot theory studies circles embedded in S3. And it turns out, and in particular, we can think of a knot as just a graph when we put vertices on the knot. And it turns out that its symmetries are much nicer in S3. And if you don't know what S3 is, you can just think of it as R3 with an additional point at infinity. And an example of why symmetries are nicer in S3 is this figure 8 knot. So I've drawn two different pictures of the same figure 8 knot. They don't look the same. But the first one, the purple one, the two ends are joined at this point at infinity. And the graph can be rotated by 180, where this point at infinity goes to itself. And so you can see this nice twofold symmetry in S3. The one on the right has a fourfold symmetry if you combine it with a reflection. But in any case, what you can see is that this nice symmetry of the one on the left, you wouldn't see it as a rotation if I put the graph in R3 rather than S3. So in general, we're going to use S3 because of the sort of extra ability to have these what we call glide rotations, which we don't have in R3. So we can define the topological symmetry group for any graph in S3, doesn't have to be a molecular graph, and it's going to be the subgroup of the automorphism group induced by homeomorphisms, and I write this pair S3 gamma to mean that the homeomorphism takes S3 to itself and takes the graph in S3 to itself. So now I'm moving far away from chemistry, thinking about this from a pure mathematician point of view, and noticing that Frucht in the 30s proved that every finite group is isomorphic to the automorphism group of some abstract graph, in fact, some connected abstract graph. And so the question that I asked was, is every finite group isomorphic to the topological symmetry group for some graph embedded in S3? So when Frucht was approaching it, he has the freedom to pick any graph, and now I've got the freedom to pick any graph and any embedding of any graph in S3. So I've got a lot of freedom. Can I do it in such a way that I'll get every possible finite group? Finite because the graphs are finite. So before I answer that question, I'm going to give you a couple examples. So here is a graph. It has a chiral knot. That is a knot that can't be deformed to its mirror image. And so that the existence of that knot means that there's no reflections of this graph to itself because of that knot. So the only thing that can happen is that the wheels, I'm calling them wheels, these circles, can rotate. They can't be interchanged because they have different numbers of rungs. So you can prove from this that the topological symmetry group, the automorphisms that are induced by homeomorphisms, is just Z2, Z3, cross Z3, cross Z4, representing the individual rotations of each of the wheels. And in fact, we can have any number of wheels, we can have any number of spokes, and we can, if two wheels have the same number of spokes, we can add chiral or not, achiral knots as we want, to the wheels to distinguish them. So here's a picture of a graph which has two wheels, each with two rungs, spokes, but they're different because one has knots, one doesn't have knots. And so the topological symmetry group of this graph is Z2 cross Z2 cross Z4. And you can see that in a similar way, I can get every finite abelian group for some embedded graph. So that's good. Check, got all my finite abelian groups. What else can I get? Well, I can actually get all symmetric groups. So here's a graph where I've put this chiral knot because I don't want to think about reflections. And I've also put this knot, this is the 817 knot, which is non-invertible, which means that it can't be deformed to itself flipped upside down with its orientation reversed, which means we can't interchange vertex V and vertex W. So the only thing we can do is interchange these n vertices with their edges along. And so we can in fact do any transposition. If I grab two of these edges like 1 and 2, I can switch their order by rotating them around vertex V and W. And so in fact, you can see that we have the entire symmetric group Sn induced by homeomorphisms of this graph in space. So on my list of all possible finite groups, infinitely many, but I've made progress. I have all my finite abelian groups. I've got all my symmetric groups. That's good. Next thing I'm going to think of is, well, what about alternating groups? That seems like a good next step. Okay, so we're thinking, well, maybe I could take this same graph and embed it differently, so I would only have even permutations and not odd ones. In fact, that's not true. So in fact, together with Ramin Naimi, Jamie Pommersheim, and Harry Tamvakis, we proved that the topological symmetry group can be an for some graph embedded somehow in S3 if and only if n is less than or equal to 5. So, and the reason, like the idea of the proof, is that we showed in general that if TSG of gamma is simple, then TSG of gamma is isomorphic to a group of orientation preserving isometries of S3, but in fact, for n bigger than 5, an can't act on S3 by isometries. And now I see Sarah lurking in the background. So what I'm going to do is I always write like my talk to be twice as long, just in case somehow time stands still and I can keep talking. But I'm going to like skip from here to my very last slide, which is going to go like this. You can't see this. You're not supposed to see it because it's too fast. And say that you should all come to our spatial graph theory session today from 1 to 5, where I've listed all of these talks that we're going to have. And you can see some words that we've already started explaining here, like topological symmetry groups and Möbius ladders, which Emil Davy-Lawrence is going to talk about, and intrinsic chirality, which we've talked about, but now we're looking at it in R3 and in other 3 manifolds, which Hugh Howards is going to talk about. And then we have some things that I have not yet introduced, but you can see that that we're going to understand better about the relationship between spatial graphs and knots in one way or another. And then there's more things which I haven't introduced, but you will see them if you come to our session this afternoon. Thank you.